right. Well, thanks for joining us tonight at Space Place. We have a guest speaker, as we do on the second Tuesday of every month. And tonight, our speaker is from the UW Astronomy Department, Scott Lucchini, who's a sixth-year grad student. So in his advanced research, in fact, I think he gets his PhD this summer. Scott came to Madison from University of Edinburgh in Scotland, where he studied physics, and then has been here keeping our supercomputing center busy on campus by figuring out how millions and millions of particles interact, or he's been making computers do that. So he's finishing up this summer, and we'll be headed out to the Harvard Center for Astrophysics in the fall, I suppose. So anyway, we're going to hear about some exciting research about how galaxies interact, and specifically our own Milky Way galaxy and some nearby galaxies called the Magellanic Streams. So join me in welcoming Scott tonight. Scott.
Hello. Thank you for the wonderful introduction. I'm Scott Lucchini. My email's up in the corner. If you have questions or want to chat or just want to say hi, drop me a line. Happy to talk about science anytime. And I'll be talking about the Magellanic Stream today. I have been working with Ellen Adongia in the UW Astronomy Department for a few years now, running computer simulations of galaxies. Two galaxies specifically, as was mentioned, the Magellanic Clouds. So here we'll get this pesky text out of the way. And this is a photo taken from Australia by Colin Legg. It's just a photograph, and it's amazing. And we can see the Milky Way on the left side here, looking edge of our own galaxy, right? This bright strip that we can see along the sky. And then these two fuzzy blobs here, this guy and this guy, these are the Magellanic Clouds. The large Magellanic Cloud on the top and the small Magellanic Cloud on the bottom. And these are other galaxies. So they're not within the Milky Way, they're outside the Milky Way. And we'll get a picture of how that all fits together shortly. But the Magellanic Clouds are super cool. They're really pretty here, and this is just optical light. You look up in the night sky in the southern hemisphere, and you'll see these guys. You got to sort of swing a little bit. You can see them. But more than the stars that we can see in this photo, what's most interesting, I find, about them is the gas that comes with them. So every galaxy is made up of stars and of gas, and this gas is mostly hydrogen, a little bit of helium, some other stuff, and gas is what collapses down and condenses and forms the stars. And so we need to know about the gas to know about what the galaxy is doing, whether it's forming new stars, whether it's dead and not doing anything at all. And so the gas is the real key to what's happening in the galaxy. And so if instead of looking up at the night sky with our naked eye, if we were to put on goggles that allowed us to see radio waves, neutral hydrogen gas emits radio waves, and so we can point our telescopes at the sky and see, well, what is the gas doing? We get a very different picture. So this is all of the gas, the neutral hydrogen, in this picture, in the night sky, from this angle. Again, we see the Milky Way disk quite strongly here, and then we still see the Magellanic Clouds, this blob here, the large Magellanic Cloud, and a small Magellanic Cloud here. If we were to get rid of all that pesky Milky Way stuff, we don't really care about the Milky Way, it's beautiful, but if we got rid of all that just to show the Magellanic gas, the gas that's with these two galaxies that are outside the Milky Way, we get this. Still a lot of stuff. So there's obviously the two galaxies that I pointed out before. It's the large and small Magellanic Clouds. There's this gas connecting the two of them, bridging the gap between them. There's this stuff trailing behind. This we call the Magellanic Stream, the trailing stream. And then all these clumps up here on the left side. This is the leading arm, and I'll go into the details of these different pieces in a few slides. But this is what I study. This crazy, huge, fascinating thing in the sky that we have no idea where it came from. We can see the Magellanic Clouds. We know there's stars, we know there's gas, we know this stuff is here, but we don't know why it's here. Where did it come from? What it's doing? And how's it going to affect the Milky Way in the future? How's it going to affect our galaxy? So my simulations are trying to answer these questions.
What's the size of these particular galaxies compared to?
Yes, that's a great question. So the LMC, the Large Magellanic Cloud on the top, is about 10% of the Milky Way in total mass. And the SMC, we don't really know, but it's probably about 10%, between And so, as I mentioned, these are galaxies outside the Milky Way. So let's take a step closer to home. Hopefully you recognize the picture. And we'll see, well, what is the Milky Way galaxy, and where are the large and small Magellanic Clouds relative to us? So here we've got Earth. This will be a movie in a second when I press go. And we're going to zoom out. We're going to zoom out from Earth and see where we fit into the Milky Way. And then we'll zoom out a little bit further to see Magellanic Clouds. So here we are. There's our moon. There's our sun coming, whizzing past. And all these other little dots are other stars in the Milky Way. And then we zoom out super big, and we see our Milky Way here. It's not a static thing. It's moving, and all of the stars are orbiting around, and it's an alive structure bound together by gravity. And we're just one of those tiny little dots way off in the corner. But then, beyond our own galaxy, this Milky Way that's made up of 100 billion stars, we can step back even further, and there's the Magellanic Clouds down below us. So here's our Milky Way galaxy, and the diameter of the Milky Way is about 100,000 light years across, so not too small. But then only 150,000 light years away are the Magellanic Clouds. They're down below us, but they're really quite close, I mean, on a galactic scale. If you think of nearby galaxies, you might think of Andromeda Galaxy. That's the nearest spiral galaxy. Andromeda is 2.5 million light years away. So these guys are 15 times closer to us than Andromeda. So they're really right next to us. They're going to impact the Milky Way a lot in the future. And so I think they're interesting to study because of that. We can learn a lot about what the Milky Way is going to be. So going back to the gas in the Magellanic Clouds, here's an image. This is another photograph, well, another hundreds of photographs stitched together covering the whole sky. So this is the entire sky in one image in what's called Galactic Coordinates. So this bright spot along the axis here, this is our Milky Way galaxy again, looking edge of it since we're stuck inside it. And then the two bright spots down here in the southern hemisphere, this is the large and small Magellanic Clouds. And now if we again put our radio goggles on, we look for where the gas is. This is the gas associated with the Magellanic Clouds, this Magellanic stream that I talked about. It is huge. So remember, this is the whole sky. So a circle is 360 degrees. This is from here, the tip of the leading arm, and all the way to the end of the stream. This is 200 degrees. So it's more than half of a circle all the way around. It's this absolutely massive structure. And again, we don't really know where it came from, so we should probably figure that out. If we zoom in a little bit, this is another coordinate system called Magellanic Coordinates. It just sort of reorients everything. It's a little bit easier to see. We can see the leading arm on the left, these clumps of gas out in front of the clouds, and then the Magellanic Clouds in the center, this bridge between them, and then the trailing stream off to the right. And so this data was taken in 2005, so it's a little bit old. It's still pretty good. You can see a lot of this interesting turbulent structure, little bumps and blobs, and these two separate filaments here in the stream. We can learn a lot from this data. But in the past, whatever it's been, 28 years, 18 years, we've come a long way. So here is some of the new data. It's not quite ready yet, but we've got the pictures of the LMC and the SMC. The rest of the stream will be coming out in the next couple of years. But these two images, I just think are absolutely amazing. Let's load them up so we can really see what they're looking like. And I promise they're better than that. Here we go. So that's photos that have been taken within the past couple of years of the gas in the Magellanic Clouds. So the left is the large Magellanic Cloud, and we can see all of these little bubbles. Those are holes in the gas because stars have exploded in supernovae and have blown all the gas nearby out. So there's these holes, and there's this bright spot on the left that's forming a lot of stars. And this is the SMC with this sort of plus shape. And again, all these little skinny filaments. I could look at these photos for hours. I just love them. Question, yes? Yeah, Mercurius. So this is the Galactic survey. So these are telescopes down in Australia. The Australian Square Kilometer Array Pathfinder is the name of the telescope. So this is, again, these are radio waves. So we can use a set of a whole bunch of telescopes working together to get this really high resolution stuff. That's called an array. So this is the square kilometer array, specifically studying the galactic gas. So this is what we have to look forward to, the whole stream in this beautiful, beautiful high resolution imagery. But right now, this is what we've got to work with. So, well, I mean, it's still pretty. So, in addition to all this gas that we've been able to image, we've learned a lot about the galaxies themselves as well. They're made up of stars, so we can track where the stars are moving. We can figure out where these galaxies as a whole are traveling. They've been approaching the Milky Way, and for a long time it was thought that they were orbiting around the Milky Way. This was one of the first theories of how this stream was formed, is if the LMC and the SMC have been coming around and around and around the Milky Way over and over, then this gas could have been pulled out from the galaxies themselves into this trailing stream over these many interactions. But we actually measured the velocities of these clouds, and they're moving really, really fast. And so now we know they couldn't have gone around the Milky Way multiple times. The Magellanic Clouds have to have been coming into the Milky Way just for the first time now. So we need a new idea for how this stream gas could have been formed, and I'll talk about a few of those in the coming slides. But these velocities of the clouds taught us something else interesting. This is why this is called the leading arm. We know these galaxies are traveling to the left. And so this gas that's out in front of the galaxies has to have come from somewhere as well. It's weird to see gas out in front. The galaxies are moving this way, and then somehow the gas gets out in front. So that's another puzzle. How can we explain how the gas got thrown out in front? And then here, this long stream is trailing behind the clouds. That will make a little bit more sense. This pink arrow is the relative velocity of the SMC with respect to the LMC, so we can see they're moving away from each other right now. And it lines up right with this high-density connection between the galaxies called the Magellanic Bridge. And so from this information, we can see that it's very likely the Magellanic Clouds had a direct collision very recently. So they've been coming in from wherever they are, and then within the past few hundred million years, very recently, I promise, they've had this direct collision. And that's brought this bridge of gas between galaxies out. There's stars in there too. And so we can learn a little bit about their history just from the velocities and the morphology, the structure of this gas as well. Yeah?
How do you know that accretion situation?
So because of the velocity, that gives us the hint, right? So if we take the positions and the velocities of the clouds and we sort of work backwards, in pretty much every case, they end up on top of each other. So that combined with the existence of this bridge seems to indicate that this was a likely thing that happened in the past. And so as I mentioned, people have been coming up with these models ever since the stream was discovered in the 70s. And as more data and more observations have come to light, we have had to adjust our models. Like I mentioned, the Milky Way, the LMC and the SMC can't be orbiting around the Milky Way many times because we learned about the velocities. And there's two pieces of observational data that I want to highlight now that have sort of thrown a wrench in all of the theories of the formation of the stream up till now. Till I did my work, obviously. But and so I'm going to highlight these two sort of mysteries, these two observational pieces of data that we need to explain as well. And the first of which is the ionization fraction. So this is another image of the Magellanic stream. This is called zenithal equal area coordinates. And the Magellanic Clouds are here in the middle. The large Magellanic Cloud and the small Magellanic Cloud, the trailing stream cloud is going upwards. And these colors represent velocity. So when we make these observations with radio waves, we can tell how fast the gas is moving in addition to what it looks like. So we know velocities of this gas. This big white stripe is the disk of the Milky Way. It gets in the way of everything. But I think some people think it's cool and study it, but it's just in my way for my work. And so from these images, we can estimate the mass of the gas that we see here. And we sort of sum up all of the gas that we see and can estimate how much is there. This is only telling us about the cold radiation for us to be able to see it. We need to detect it indirectly. So that's where absorption line spectroscopy comes in. In order to see this hot gas, we need to pick something in the background, a bright star, or often a very bright galaxy called a quasar, an active galaxy. And we know what that background source is supposed to look like. Right? You know, if you take a prism and shine sunlight through, you'll see all the rainbow colors, right? Just like this figure here. We know that we're supposed to get all the colors from one of these background sources. But if we look at that source and we measure its spectrum, that's looking at the intensity of the light as a function of wavelength, and we're missing some pieces, like this black lines, we're missing these pieces, we know there's something in between us and that source that absorbed that stuff. And so we can figure out what it is. Based on what frequencies are absorbed, we can figure out what the different elements are in that gas and what temperatures they're at. And so using this technique, we see this blob of gas absorb this little bit, this blob of gas absorb this little bit, and we can learn about what these blobs of gas are composed of. And so that's what we did around the Magellanic stream. We took, I think it was 28 or 30 of these background sources and tried to see, is there hot gas there too? We know there's the cold gas because we can look up and see it. But is there also hot gas? And the answer is yes, and a lot of it. So we know that this is stuff that's associated with the Magellanic stream because those colors are the same colors as the cold gas. So this stuff is moving at the same speed as the neutral, the cold gas that we can see. And if we sort of sum up the total mass that we'd expect the hot gas to make up, it's 84% of the total mass. So what we can see in this neutral hydrogen emission is only a tiny fraction of what the Magellanic stream is actually made up of. So we have this now total mass of this Magellanic stream of up to 2 billion solar masses, 2 billion times the mass of the sun. That's a lot of gas that we now have to account for. We've got to figure out, well, where did this hot gas come from too? We know we've got to figure out where the cold gas came from, but now we need a whole story to explain both of these pieces. So that's mystery number one. Mystery number two involves the mass of the LMC. So masses of galaxies is tricky because masses of galaxies are tricky. Well, one of the two. Because there's a lot of stuff that we can't see. If we look at a star that's traveling around in a galaxy, right? I mentioned from that video at the beginning, galaxies are moving things, right? The stars are all orbiting around the center of the galaxy. If we say take a star out here and we see how fast it's going pretty fast. That's this green line at the top. But if we were to take that star and calculate how fast should it be going based on Isaac Newton's gravitational forces, we sum up all the forces between it and all the other stars and gas that we see. We think, well, no, it should actually be going very slowly, this yellow line. So what's the problem? There's something missing. There's some amount of mass that we haven't summed up in our gravitational calculations, and that's dark matter. So perhaps you've heard of dark matter. It's the stuff that we can't see that holds the galaxy together. So we can't see it in light emission in any way. It doesn't interact with stuff as far as we can see, but it has mass, and so it provides gravitational force. So we can detect it indirectly. And so if we can, so now we have this picture of a galaxy that has stars and gas in this disk in the middle, but then it's embedded within this halo, this spherical halo of dark matter, sort of glues it all together and makes sure it doesn't explode. So in order to determine how massive a galaxy is, we need to figure out, well, how much dark matter is there? And so if we look out at these large distances, we can see how fast things are actually moving compared to how fast we'd expect things to move, and voila, we can just figure out what mass is missing. The problem is the LMC is like this tiny little thing. So the speed that we see things moving at and the speed things should be moving at are pretty much the same. So we can't really get a good measure of how massive the LMC is because it's so small. And the SMC bottom one, so here's the references if you want to go look up and read a technical paper, you're welcome to go do that. And this is how they figured it out on the right. This bottom one is the technique I just mentioned. So they look at a star, see how fast it's moving, and they get a very low mass. This is very, on the left side of the plot means it's very low mass. All these other methods find a mass that's very high. This value is at 10% of the Milky Way that I mentioned earlier. So it seems like a lot of these methods are converging on a similar value that is quite high. This one I'll talk about in a second. That's the outlier. It seems like it shouldn't be there. So these are the two mysteries that have sort of prompted my work, and this is the reason I'm running these simulations. One, we have to explain this hot gas and the cold gas, and we need to do so while using a large LMC, right? We're looking at how these galaxies have been evolving over time, so we need to know what mass to start with for the LMC to see how they've been interacting. Yes?
So, is there like a very high variability in the ratio of dark matter to visible matter in galaxies? That makes it so you can't
Oh, yes.
interpolate or
Yes. So the question was, is there a very high ratio between baryonic observable matter and the dark matter, or does it vary a lot, but from galaxy to galaxy? And it does. So there's sort of an approximation that you can make. It's called abundance matching. It's up there, the number 4 on the way down. So you can approximate how much dark matter there should be based on the stars and the gas that you see. It's just that. It's an approximation. And because the LMC and SMC have been interacting, maybe it's not right, but maybe it is. So it does seem to align with these other estimates, so it probably has some weight to it. But the specific structure of the dark matter really depends from galaxy to galaxy, so it's quite tricky to determine. So each of these puzzles, these mysteries, have been sort of figured out separately. So we can explain this ionized gas by itself. But this requires a very low mass for the LMC. There's the outlier, this guy there. So this technique, we have the LMC and the SMC, and they're approaching the Milky Way, right? But they're not just falling in and floating into the Milky Way, they're pushing through additional gas. So the Milky Way has its own dark matter halo around it, but it also has a halo of hot gas. And so the LMC and the SMC have to push through that gas as well. And this is like, say you're biking down by the lake and it's a windy day, you have to bike a lot harder because the wind's blowing at you, right? So your hat flies off because the wind's blowing so hard. That's this ram pressure force. The LMC and SMC are pushing through this hot gas, and their hats are flying off. All the gas that's in the disk is being pushed out behind them into this stream here. So the colors are the results of the simulation compared with the observations in black here. And this gas that's been pushed out behind is because it has to move through this hot gas medium. But in order for the gas to get pushed out easily, it needs to have a low mass. Otherwise, the gravity is hanging on too tight, and nothing gets spread out into this trailing stream. And so because the gas is getting pushed out so strongly, a lot of it gets heated up, and we get this hot component sort of surrounding, that's what's shown in this top plot, this hot component sort of surrounding this cold neutral bit. So we can explain where this hot gas came from, but it doesn't work with this high LMC mass. Similarly, we can explain the formation of the stream with a high LMC mass, but it doesn't explain any of the ionized gas. So in this case, we have the LMC and the SMC orbiting around each other. They're dancing around each other, and as the SMC comes around the LMC, the gas in the SMC gets thrown out to the side. This one's like you're driving down the street and you take a hard left. Everybody in the car gets thrown to the right. Yeah, the centrifugal force. I never know which one's right. But because of this SMC having a sharp acceleration as it orbits around the LMC, the gas feels this centripetal force and gets thrown out to the side. And so we can explain the leading arm here and the trailing stream, but we only get the cold gas. So how do we fix this dilemma? So this is my work here that I've been doing at UW-Madison here, and we've introduced this thing called called the Magellanic Corona. So like I mentioned, the Milky Way has its dark matter halo, and it has a halo of gas as well. We think that galaxies above a certain mass, large galaxies, should always have this halo of gas. And because the LMC now seems to be a massive galaxy, we think it should have a halo of gas as well. And so down in the bottom right, you can see a sort of schematic view of the LMC galaxy in the middle, surrounded by this fuzzy sphere of hot gas. And this is called the Magellanic Corona. And we think, as I mentioned, we think this should be here because the mass of the LMC is high enough. And if we look at cosmological simulations, these are super cool. These are simulations of a significant chunk of the universe from beginning to end, essentially, well, not to end, to now. But they're looking at how galaxies and stars form all self-consistently. So it starts from very early on in the universe to see how these galaxies form. And if we look at galaxies like the LMC, we see the gas around them. So based on our models of how the universe evolved, this gas should be here. And if we actually look at the LMC today, we look up in the sky, on the face of the LMC, we can use more of this absorption line spectroscopy to detect if there's this hot gas around the LMC itself. And we do see a lot of ionized gas. We're not sure if it's in the disk or in this sort of corona yet, but there's a lot of ionized gas, so it's promising. The question then is, when we include this Magellanic Corona in our model, can we explain the data? So now we have this picture of LMC and SMC. They're doing their dance. They're orbiting around each other just like before in the tidal model on the right that I showed. But they're doing this while embedded within the Magellanic Corona that sort of then envelops the tidally stripped material that we saw before. We have this envelope of hot gas, warm gas, that should theoretically explain predictions. And so I tested this. I ran computer simulations to see if this works. So now we get to the fun part of the talk where you get to see all of my fun movies. So this is going to be one of my simulations, the first half of one of my simulations. The LMC is this stripe in the center. We're looking at the galaxy edge on, so that's why it looks like a line and not a circle. Similarly, here's the SMC. It is a circle if you look at it that way, but we're looking at it edge on. And then here's the Magellanic Corona, this sphere of gas surrounding the LMC. So let's see what happens. So there you see one of those tidal interactions that I mentioned. That's when the SMC turns left and the gas goes right. All of this material that's been tidally stripped, it's been thrown out of the SMC because of that interaction here, where the SMC comes around and the gas goes out. All the while, we're embedded within this sort of fuzzy purple stuff. That's the Magellanic Corona that's surrounding this whole endeavor. This isn't quite present day yet. Remember, I mentioned that LMC and SMC are just approaching the Milky Way now, just recently. So this was 5.5 billion years of evolution. The last 1 billion was when they're coming to the Milky Way. So let's look at that now. So we sort of reorient our frame of reference. The Milky Way is this gray oval in the middle, and this is the LMC and the SMC from before. We sort of turned everything around, and now they're coming and approaching the Milky Way, and let's see what happens here. So we have a few more interactions between the clouds, but this material that was the tidally stripped material before stays here, and we've got all of this other gas, coronal gas surrounding it. So now, what does this look like from Earth? This is sort of a zoomed out Cartesian coordinates view. What does this look like from Earth? And here now we're comparing with our observations, again with contours. This is the plot that I showed you right at the beginning, the low resolution old one, right? And the top is showing all the gas, including the ionized stuff. And there's ionized hot gas everywhere, so that's good. And the bottom is showing the neutral stuff that we're supposed to compare with this contour, this line. And we see there's sort of a tail, it's a little bit long, and doesn't really look right, but it's there. We've got gas. And we've got some stuff out on the left in this leading arm region as well. So we've more or less been able to form this stream, but is there enough gas? That was one of the big questions, right? There's so much of this hot gas. Do we solve the problem? And the answer is This on the left is the previous model. No Magellanic Corona. We get the neutral material stripped out, the cold gas stripped out, just like we see in the observations, but there's no hot gas on top of it. The model on the right includes everything, and so this orange stuff is the material from Magellanic Corona that was ionized and is hot and should be able to reproduce those observations that we had. And then if we also assume maybe a little bit of this material that came out of the SMC we saw when it got tidally stripped, if some of that gets heated up because it's colliding with stuff as well, then we get our ionization fraction of about 77%. We're comparing with 80 or 84%. So it's not too bad. It works. And the total mass is up at above 1 billion solar masses. Here's 1 billion solar masses. It's about 1.3 billion solar masses. So it seems to fit the bill. And this was published in Nature. I have to plug my work a little bit. It was very exciting. We got on the cover, actually, back in September of 2020. And so this was a very exciting way to kick off grad school. But there were still a few problems with this model. So as I mentioned, this neutral stream, this cold gas, doesn't look very good. It's all smooth. It's way too long. It doesn't really match the observations in terms of morphology, in terms of the way it looks very well. And additionally, the LMC and the SMC here, they've had a few extra interactions, and they've actually ended up on top of each other. And we know the LMC and the SMC, we can see them as two separate galaxies on the sky today, so we know they're not on top of each other. So we need to fix these two things with our future models, or well, what were the future models that I'm going to show you now. We need the stream to look a little bit better, and we need the galaxies to not be on top of each other. So we found a new history, an alternative history for the clouds that hopefully will do a better job. So the models that I showed you at the beginning, we have the LMC and the SMC interacting for 5.5 billion years, and then falling into the Milky Way for another 1.5 billion years. So this is a really long history. And once we include the Magellanic Corona, the SMC has to push through all of that Magellanic Corona gas in addition to pushing through all of the Milky Way gas. So it's really getting slowed down. So that's why they ended up on top of each other. Because the SMC, the orbit of the SMC is decaying. It's pushing through too much gas, and it ends up just falling on top of the LMC. So we need a shorter history. So we're cutting out that first half. We're just looking at the LMC and the SMC falling into the Milky Way now. We're covering about 3.5 billion years instead of 7. And we'll see what we end up with. So again, here's our Milky Way edge on. Here's the SMC, and the LMC, you can see the Magellanic Corona, the edge of it here. The LMC is just off the edge, just going to say. So there's the LMC. And the SMC does its loopy-loop again, and we see this material stripped off. This is the tidal interactions that are stripping the cold gas out of the disk. All the while, this big, huge halo of Magellanic Corona is coming along with us. And so we have this neutral material that's embedded within this large Magellanic Corona. So it's the same picture as before, it's just a slight tweak, so that we end up with the LMC here and the SMC here. They're separated now at the present day in agreement with the observation. Their velocities are correct as well. That was one of the tricky parts, making sure they're moving at the right speed. Let's take another look at this. This one's just showing the neutral gas, just the cold gas. The Magellanic Corona is still there, but we're just not showing it, so you get to see what these tidal interactions are really doing. So the SMC has this sort of loop-de-loop, and that's where this material gets thrown out. And if you notice this right here, this collision is the recent collision that I mentioned right at the beginning, where the SMC punches right through the LMC and forms that bridge of gas and stars in between the galaxies today. So that's the bridge that's formed right by that most recent interaction. And so now we have this model that seems to reproduce the high mass of the LMC, the ionized gas, the hot gas, and the cold gas, and the positions and the velocities of the cloud. So it seems like we're doing okay. Let's now take a look at it from Earth. We'll take some sort of mock observations, they're called, to see what we can learn from these simulations in this model. So we started with this data. This is again the zenithal equal area coordinate colored by velocity. And what did we start with from this data? We learned about the galaxies. We learned about where they are, how far away they are, how fast they're moving. don't get the same type of picture from the cold gas because we have to use the absorption line spectroscopy technique. But we know where it is on the sky, we know how much is there, and we know how fast it's moving. But there's a few key things that we don't know, and we can't learn from the observations. One is how far away is the gas. This one's actually puzzling. We can never actually find the distance to gas in astronomy. The only way we know how to find distances is by looking at stars, or velocities very, very far away. And so there's no stars in the trailing stream, so we don't know where the gas is. We don't know how far away it is. And we don't know where it came from. As I mentioned before, one of the main reasons we want to do this modeling is to explain where this gas came from and what happened so that it looks like this. And we want to also know what the hot gas looks like. We only have these pinpoint pictures of where the hot gas is. So now we have our simulation, and hopefully we can learn some of these things and make some predictions. So this on the right is now the result of our simulation. We've got the LMC here and the SMC here, and this is our trailing stream. And the morphology looks a lot better. We have this sort of filamentary, little bubbly, turbulent structure that matches what we see in these observations much better than the previous model did. So we had that one smooth tidal tail before that didn't look very good. Now we have this sort of more intricate structure that agrees with the observations better. And so we can now directly compare the simulations with the observations. This is what the whole cold gas looks like, and as I mentioned, the morphology, the small turbulent filamentary structure looks pretty good. There's this weird bubble, and again, it's too long, but hey, it can't be perfect. And then we know how fast the gas is moving from the observations, and so we can compare our simulations with that. This is the velocity as a function of this, what's called Magellanic longitude. And we see the gray background lines up with the contours very well. So our simulation and the data agree. So now we can move forward and make predictions. This is what the hot gas looks like. And so, because simulations are great, we know everything, and we can make predictions. Well, I think the hot gas is higher density here and lower density there. And we can try to make some more observations to test that. Well, is this actually what the hot gas looks like? And similarly, we can look at how far away the gas is. This was one of the main results of this second paper that I published. The gas in the stream, this is the distance away from us along the length of the stream again. It's actually really close. So the Large Magellanic Cloud is 50 kiloparsecs away. That's 150,000 light years I mentioned at the beginning. This gas is 20 kiloparsecs away, half the distance to us. It's closer to us than the galaxy is. So this is really confusing. It has a lot of interesting implications. But since it's so close, we might actually be able to test this. We can use this absorption line spectroscopy technique again. If we look at a star instead of a galaxy that's really far away, if we use a star we know the distance to, and we see this gas in between us and that star, then we have a distance constraint. We know the gas is closer to us than that star. And 20 kiloparsecs is close enough that there are some stars further away. So we're testing this now. This model made this prediction that the gas is actually really nearby, and so we're now going to make new observations to see if it's true, and see if we can corroborate this data, or if we need to start back again from square one. So this is what I want to leave you with today, is sort of the life cycle of research as a simulator. So we start with observations. As I mentioned, we learn about the galaxies and the gas and what it looks like and what we need to match. Then we make our simulations, and we can then learn things from the simulations, where the gas came from, where it's going, how it's going to affect the Milky Way in the future, how far away is the gas, and where the hot gas is. All these types of things we can now learn, and then we go back to the observations, and we make new observations to try to confirm these predictions and test our model. And if there's something that doesn't quite work right, then we go back and try our simulations again, tweak the models, and see if we can eventually come up with a model and a simulation that fits all of the observations and makes new predictions that are then proven true. And so that's where the trajectory that my research has taken, and I think it's really interesting to be able to make these predictions and see if we're right. Maybe we're not, maybe we are. But that's what